Okay, so you've probably heard of quantum mechanics.
Yeah, definitely.
Maybe just in passing is this weird thing that happens to tiny things.
Right.
But we're diving headfirst into that weirdness today because it turns out this quantum realm,
Yeah.
it governs everything from molecules to atomic nuclei. It's the fundamental rule book of reality. Forget about how things work on a day-to-day basis.
Yeah, exactly.
How at the smallest scales, it's a whole new ball game.
It really is. And in this deep dive, you and I are going to unpack the core ideas of quantum mechanics as presented in this material.
Okay.
Our mission is to give you a clear understanding of wave functions, the Schrödinger equation, and the quantum phenomena that they unlock.
Perfect.
Think of it as getting the essential insights into how the universe truly ticks at its most basic level.
Okay, so the absolute key to understanding quantum mechanics is this.
Okay.
It uses a wave picture to describe particles.
Yeah.
I mean, let that sink in for a moment. We're not talking about billiard balls or tiny marbles. We're talking about entities that behave like waves.
Right.
This wave-like nature is the key to all the quantum weirdness. Let's start by looking at these things called wave functions.
Okay.
What exactly are they?
So in the classical world, to describe a particle, you'd specify its position and momentum.
Right.
But in quantum mechanics, a particle state is far more nuanced.
Okay.
And it's encapsulated by its wave function, which is symbolized by the Greek letter Ci.
Okay.
For a particle moving in one dimension, this is LAA of x and t.
Got it.
Think of it as a mathematical description that holds all the knowable information about that quantum particle. Its energy, its momentum, and the probability of finding it at a particular location at a given time.
All the knowable information. That's a pretty heavy lift for a single function.
Yeah, it is.
So how do we extract that information? How do we know what the particle is doing based on its wave function?
Well, the wave function's behavior is governed by the fundamental law of quantum mechanics. This equation is the quantum equivalent of Newton's laws in classical mechanics. It tells us how the wave function evolves over time under the influence of different forces or potential.
Okay.
In one dimension, the time-dependent Schrödinger equation looks like this. Negative parenthesis h bar squared divided by 2x parenthesis times the second partial derivative of a with respect to x plus u of x times a of x and t equals I h bar times the first partial derivative of a with respect to t.
Wow.
Yeah.
Okay, that equation looks intimidating.
Or,
Let's break down what's really important here. What are the key players in this quantum rulebook?
Absolutely. The equation essentially describes the interplay between a particle's energy and its wave-like nature.
Okay.
H bar is the reduced Planck constant. It's a fundamental constant that tells us that energy in the quantum world comes in discrete packets. It is the particle's mass.
Right.
And x represents the potential energy it experiences at a certain position. The term with the second derivative of with respect to x is related to the particle's kinetic energy.
Right.
Its energy of motion.
Got it.
On the other side is the imaginary unit, and the derivative of with respect to time tells us how the wave function, and thus the particle state changes over time.
Okay.
So the Schrödinger equation is the dynamic rule that governs how a quantum particle's wave evolves based on its energy environment.
Okay, so we have this wave function that describes the particle, and the Schrödinger equation tells us how it changes.
Right.
But how do we get from this waves description to something we can actually observe, like where the particle is?
So that's where the concept of probability comes in.
Yeah.
The probability of finding a particle in a specific region of space at a given time is determined by the square of the absolute value of the wave function, the absolute value of x and t squared.
Okay.
This is the probability distribution function. If the wave function is a complex number, say a plus ib, then the absolute value of s squared is simply a squared plus b squared.
Right.
What's crucial is that while the wave function itself can be a complex entity, the probability we observe is always real and positive.
Okay.
So a higher value of the absolute value of x and t squared in a particular location means a greater likelihood of finding the particle there.
So high peaks in that absolute value of x and t squared landscape tell us where the particle is most likely to be.
Exactly.
What happens if a particle isn't subject to any forces? What if u of x is 0?
In that scenario, we have what's called a free particle.
Okay.
The Schrödinger equation simplifies, and one possible solution is a sinusoidal wave. X of x and t equals a times e to the power of I parenthesis kx minus omega 2 parenthesis.
Okay.
Here a is the wave's amplitude, k is the wave number.
Okay.
which is related to momentum by P equals h bar k.
Right.
And omega is the angular frequency,
Okay.
which is related to energy by E equals h bar omega.
Got it.
The fascinating thing here is that this single, perfectly smooth wave represents a particle with a precisely defined momentum and energy.
But if we know the momentum and energy, that precisely what does that tell us about the particle's location? There's a trade-off, right?
Exactly. The Heisenberg uncertainty principle kicks in.
Okay.
If you have perfect certainty about a particle's momentum or energy, you have infinite uncertainty about its position or the time at which it possesses that energy.
Okay.
This single sinusoidal wave extends infinitely in space.
So it's everywhere and nowhere simultaneously.
Exactly. It's everywhere and nowhere simultaneously, meaning its position is completely undefined.
So a single perfect wave doesn't really describe a localized particle that we can pinpoint.
Right.
How do we reconcile the wave nature with the fact that we observe particles in specific places?
That's where we use the principle of superposition to build what are called localized wave packets.
Okay.
Imagine you have many individual waves, each with slightly different wave numbers and frequencies, and you add them all together in a specific way. They interfere with each other, and in one region they constructively interfere to create a peak, while elsewhere they destructively interfere and cancel out.
Okay.
This localized blip of wave energy is the wave packet, and it represents a particle that is now confined to a certain region of space.
That makes intuitive sense.
Yeah,
A localized wave packet sounds much more like a particle.
exactly.
But what's the catch?
The catch is that the trade-off lies directly in the uncertainty principle.
Okay.
The more tightly you confine the wave packet in space, a smaller delta x, the wider the range of wave numbers delta k you need to create it.
Okay.
And since momentum is related to the wave number p equals h bar k, a wider range of delta k means a greater uncertainty, and the particle's momentum delta p is greater than or equal to h bar divided by 2 delta x.
Okay.
Also, unlike light waves, where all frequencies travel at the same speed in a vacuum, the speed of a matter wave depends on its wavelength. This means that the different wave components within the wave packet travel at slightly different speeds, causing the wave packet to gradually spread out over time.
Okay. That's the free particle.
Right.
Now let's consider what happens when we confine a particle. A classic example is the particle in a box.
Yeah.
What's that all about?
So the particle in a box is a fundamental model where we imagine a particle trapped within a one-dimensional region of length L.
Okay.
At the boundaries, x equals 0 and x equals L, there are infinitely high potential energy barriers.
Okay.
So it's like the particle is stuck inside an infinitely deep well.
Right.
Inside the box, the potential energy of x is 0.
Got it.
Because the walls are impenetrable, infinite potential, the probability of finding the particle at the walls must be 0.
Okay.
Which means the wave function psi of x must be 0 at x equals 0 and x equals L.
Okay.
These are our crucial boundary conditions.
So we take the Schrödinger equation set x to 0 within the box and then apply these can't be at the walls rules.
Right.
What kind of solutions do we get?
So solving the time-independent Schrödinger equation, which is negative parenthesis h bar squared divided by 2v or a parenthesis times the second derivative of psi I with respect to x equals e times ci of x for this specific case, while adhering to the boundary conditions leads to a remarkable outcome.
Okay.
The particle's energy is quantized.
Yeah.
It can only exist at specific discrete energy levels given by the formula E sub n equals parenthesis n squared pi squared h bar squared parenthesis divided by parenthesis 2 ml squared parenthesis, which also equals n squared times parenthesis h squared divided by 8 ml squared parenthesis, where n is a positive integer, 1, 2, 3, and so on.
Okay.
This n is our first quantum number, and it dictates the allowed energy states.
Quantized energy levels. That's a huge departure from our everyday experience, right?
Absolutely.
A regular-sized object in a box could have any amount of energy.
Precisely.
Yeah.
And notice that the energy levels are proportional to n squared. This means the higher the quantum number, the greater the energy, and the spacing between consecutive energy levels increases as n grows.
Okay.
Along with these discrete energy values, we also find the corresponding wave functions, the stationary states.
Okay.
CO sub n of x equals the square root of 2 divided by L times sine of n pi x divided by L for 0 less than or equal to x less than or equal to L and 0 elsewhere.
Okay.
These wave functions represent standing waves inside the box, much like the vibrations of a guitar string fixed at both ends.
Right.
For each allowed energy, E sub n, there's a specific wave pattern, T high sub n of x, with n half wavelengths fitting perfectly within the box's length L.
And the lowest energy state when n equals 1, that's the ground state.
Exactly.
The particle can't have zero energy even when confined.
Exactly. The n equals 1 state is the ground state, the minimum possible energy the particle can possess within the box.
Okay.
States with n greater than 1 are the excited states.
Right.
Now, if we look at the probability distribution, the absolute value of I psi sub n of x squared equals 2 divided by L times sine squared of n pi x divided by L.
Oh, yeah.
You'll notice that the probability of finding the particle at different points inside the box is not uniform. In fact, for certain energy levels, there are specific locations within the box where the probability of finding the particle is absolutely 0.
Wow.
And you're right, the lowest energy, E sub 1, is greater than 0.
Right.
This minimum energy is a direct consequence of the uncertainty principle.
Okay.
Because the particle is confined to a finite space, delta x equals L, its momentum cannot be exactly 0, implying it must have a non-zero kinetic energy.
Okay, so the infinitely deep well gives us these neat quantized energy levels.
Right.
But what if the walls aren't infinitely high?
Yeah.
What if we have a more realistic scenario, a finite potential well?
So a finite potential well is indeed more physically relevant.
Okay.
Imagine a well with a certain depth, U sub 0, and a width, L. The potential energy of x is negative U sub 0 inside the well.
Right.
For 0 is less than x is less than L, and 0 outside.
Okay.
Now, if a particle's total energy E is negative, according to our convention, it can be in a bound state, meaning it's likely to be found within or near the well.
How do the wave functions behave differently in this case compared to the infinite well?
Yeah.
Do they just suddenly drop to 0 at the edges?
Not quite. Inside the finite well, the wave functions are still sinusoidal in nature, reflecting the oscillatory behavior of the particle.
Okay.
However, outside the well, where the potential energy is 0 and the particle's energy E is negative, the Schrödinger equation yields solutions that are exponentially decaying. This means that the probability of finding the particle extends beyond the physical boundaries of the well, although it decreases rapidly as you move further away from the well.
So there's a chance, however small, of finding the particle outside the well, even if it doesn't have enough classical energy to escape. That's another very quantum mechanical idea.
Precisely. And unlike the infinite well, a finite potential well only supports a finite number of bound states.
Okay.
The exact number depends on the well's depth, U sub 0, and width L. Furthermore, there's no simple algebraic formula for the allowed energy levels.
Okay.
Instead, they're determined by solving a transcendental equation that arises from the crucial requirement that the wave function and its first derivative must be continuous at the boundaries of the well.
Right.
X equals 0 and x equals L. This ensures a smooth and physically realistic wave function.
Okay.
Interestingly, the energy levels in a finite well are always lower than the corresponding levels in an infinitely deep well of the same width because the particle has a greater spatial extent.
Right, because the wave function leaks out a bit, effectively making the space the particle occupies larger.
Exactly.
Now, what if instead of a dip in potential energy, we have a bump?
Yeah.
What if the potential energy goes up in a certain region, creating a barrier?
That leads us to one of the most counterintuitive quantum phenomena.
Okay.
Tunneling. Imagine a potential barrier with a certain height, U sub 0, and a width, L.
Okay.
Now consider a particle approaching this barrier with an energy E that is less than U sub 0.
Okay.
According to classical physics, if the particle doesn't have enough energy to climb over the barrier, it will simply bounce back. It will be reflected.
But quantum mechanics offers a different possibility.
Yes.
The particle might just go through.
Exactly. In the quantum realm, there's a non-zero probability that the particle can actually penetrate and emerge on the other side of the barrier, even if its energy E is less than the barrier height, U sub 0. This is quantum tunneling.
That sounds like magic. How can a particle seemingly violate the conservation of energy and pass through a barrier it doesn't have enough energy to overcome?
It doesn't actually violate energy conservation.
Okay.
The key is the wave nature of the particle.
Okay.
The wave function doesn't just abruptly stop at the barrier.
Okay.
Instead, it enters the barrier and decays exponentially within it. If the barrier is sufficiently thin, the wave function can still have a small but significant amplitude on the other side.
Okay.
This non-zero amplitude corresponds to a probability of detecting the particle beyond the barrier.
And the likelihood of this tunneling happening depends on the characteristics of the barrier itself.
Absolutely. The probability of tunneling, quantified by the transmission coefficient T, is extremely sensitive to both the width L and the height U sub 0 minus E of the potential barrier.
Okay.
A wider or higher barrier results in a much lower probability of tunneling.
Right.
Mathematically, the transmission coefficient is approximately given by T is approximately equal to G times E to the power of -2 kappa L, where G is a factor that varies slowly with energy, and kappa equals the square root of parenthesis 2 meter times parenthesis U sub 0 minus E parenthesis divided by H bar.
Right.
Notice the exponential difference on the barrier with L and the square root of the difference between the barrier height and the particle's energy.
So even if the probability is minuscule, it's not zero. This seemingly bizarre phenomenon must have some significant real-world applications, right?
Indeed. Tunneling is not just a theoretical curiosity. It's a fundamental process that underlies many important phenomena. For instance, it's crucial for alpha decay, where an alpha particle tunnels out of an unstable atomic nucleus.
Wow.
It's also the operating principle behind scanning tunneling microscopes, or STMs,
Okay.
which allow us to image surfaces at the atomic level by measuring the tiny tunneling current between a sharp tip and the surface.
Okay.
Even in biological systems, quantum tunneling is thought to play a role in speeding up certain enzymatic reactions.
It's incredible to think that this seemingly impossible quantum trick is essential to so many different processes.
It really is.
Now let's move on to another key system in quantum mechanics, the harmonic oscillator.
Okay.
What's the quantum take on that?
So the quantum harmonic oscillator is a model that describes systems experiencing a restoring force proportional to their displacement from an equilibrium position. Think of a mass attached to a spring.
Right.
The potential energy for a classical harmonic oscillator is given by U of x equals 1/2 k prime x squared, where k prime is the spring constant.
And when we apply the Schrödinger equation to this potentialator,
Yeah.
what do we find about the energy levels? Are they quantized as well?
Yes. Once again, we find that the energy levels are quantized.
Okay.
For the quantum harmonic oscillator, the allowed energy levels are given by E sub n equals parenthesis n plus 1/2 parenthesis times h bar omega, where n is now a non-negative integer, 0, 1, 2, and so on. And omega equals the square root of k prime divided by m is the classical angular frequency of the oscillator.
Notice that here, the quantum number n starts at 0, unlike the particle in a box.
Yeah.
And what's the significance of that extra plus 1/2 in the energy formula?
That plus 1/2 is profoundly important.
Okay.
It signifies that even in the lowest possible energy state, the ground state n equals 0, the quantum harmonic oscillator still possesses a non-zero energy. E sub 0 equals 1/2 h bar omega. This is known as the zero-point energy and is another direct consequence of the Heisenberg uncertainty principle.
Right.
If the oscillator were perfectly at rest at its equilibrium position with zero energy, we would know both its position and momentum with perfect precision, which is forbidden by the uncertainty principle.
Okay.
Furthermore, the energy levels for the harmonic oscillator are equally spaced by an amount h bar omega.
That equally spaced energy ladder seems like a particularly elegant result.
Mm-hmm.
What do the wave functions look like for the harmonic oscillator?
So the wave functions psi sub n of x for the harmonic oscillator are mathematically more intricate than those of the particle in a box.
Okay.
They involve Hermite polynomials multiplied by a Gaussian function.
Okay.
And similar to the case of the finite potential, well, there's a non-zero probability of finding the particle in classically forbidden regions. Areas where the potential energy 1/2 k prime x squared is greater than the total energy E sub n.
Okay.
However, there's a beautiful connection to the classical world here. As the quantum number n becomes very large, the quantum mechanical probability distribution for finding the particle starts to closely resemble the classical probability distribution for a harmonic oscillator,
Okay.
where the particle spends more time at the extremes of its oscillation.
Okay.
This is a manifestation of the correspondence principle, which states that in the limit of large quantum numbers, quantum mechanics should reproduce the results of classical physics.
Okay. We've covered wave functions, the Schrödinger equation, and some crucial quantum systems, the particle in a box, potential wells and barriers leading to tunneling, and the harmonic oscillator.
Right.
But there's one final, really strange aspect of quantum mechanics we need to touch on: the role of measurement. How does the act of observing a quantum system affect it?
Yeah.
It seems fundamentally different from how we measure things in classical physics.
Yeah, you've hit on a core and often debated aspect of quantum mechanics. In
Right.
classical physics, measurement is generally considered a passive process.
Right.
We observe a system without fundamentally altering it.
But in the quantum realm, the act of measurement can have a dramatic and instantaneous effect on the state of the system.
Earlier, you mentioned something called wave function collapse.
Yeah.
What exactly happens when we measure a quantum property?
So if a particle's wave function is in a superposition,
Okay.
meaning it exists as a combination of multiple possible states for a particular property, like momentum or energy,
Right.
the act of measuring that property forces the system to choose one of those definite states.
Okay.
This abrupt transition from a superposition to a single state is what we call wave function collapse.
Okay.
The outcome of the measurement is probabilistic. We can't predict with certainty which state the system will collapse into.
Okay.
Instead, the probability of measuring a particular value is determined by the coefficients associated with that state in the original superposition. Specifically, it's proportional to the square of the magnitude of that coefficient.
Can you give us a concrete example of this wave function collapse in action?
Sure. Let's go back to our particle in a box.
Okay. If the particle is in one of its stationary states, say psi sub n of x, it has a definite energy E sub n. If you measure its energy, you will always get E sub n, and the wave function remains psi sub n of x.
Right.
However, imagine the particle's wave function is a superposition of two different stationary states,
Sure.
say I sub 1 of x and Cs sub 2 of x.
Okay.
Before you measure the energy, the particle doesn't have a definite energy.
Okay.
It's in a combination of both E sub 1 and E sub 2.
Right.
But when you perform an energy measurement, you will randomly obtain either E sub 1 or E sub 2 with probabilities determined by how much of psi sub 1 of x and psi sub 2 of x were present in the initial superposition.
Okay.
Immediately after the measurement, the wave function will have collapsed into either psi sub 1 of x or psi sub 2 of x, corresponding to the energy value you just measured.
Okay.
Subsequent energy measurements will then yield the same value.
So the very act of looking at a quantum system, of trying to gain information about it, forces it to snap into a definite state.
Yeah.
That's a really mind-bending departure from our classical intuition.
It is indeed. And it underscores the inherent probabilistic nature of quantum mechanics when dealing with systems that are not indefinite eigenstates of the property being measured.
This has been an incredible journey into the foundational concepts of quantum mechanics.
Yeah.
This material provides a solid framework for understanding the truly bizarre and fascinating world at the atomic and subatomic levels. And as a valuable resource for solidifying your understanding, you, our listener, have access to a comprehensive glossary of key terms, from wave function to tunneling and superposition.
Yeah.
It's definitely worth reviewing to ensure these concepts are clear.
Absolutely. Having a firm grasp on this vocabulary is essential for navigating the more advanced topics within quantum mechanics.
So to bring it all together, we've explored how quantum mechanics fundamentally describes particles as waves governed by the Schrödinger equation. We've seen how probability becomes a central element in predicting the behavior of these quantum entities. We've delved into the quantization of energy in systems like the particle in a box and the harmonic oscillator. We've marveled at the seemingly impossible phenomenon of quantum tunneling.
Right.
And finally, we've grappled with the unique and impactful role of measurement in the quantum world.
And as you consider these ideas, remember that these aren't just abstract mathematical concepts. These are the underlying principles that govern the behavior of all matter and energy in the universe at its most fundamental level.
Wow.
The implications are far-reaching and continue to shape our understanding of reality.
It really does make you think about the nature of reality itself, doesn't it?
It does.
How do these probabilistic ways at the smallest scales give rise to the seemingly concrete and deterministic world we perceive?
Yeah.
It's a profound question to ponder. We hope this deep dive has provided you with a solid foundation in these essential quantum concepts.
I agree.
Thanks for exploring this fascinating realm with us.